Let's now start with 1 electron per unit cell or 1 electron per site. So Z will be 1 in this expression for Kf, and so the radius in this case, the radius of the Fermi circle would be small, so that it fits entirely within the first Brillouin zone, and therefore the reduced zone scheme also looks quite trivial. There's nothing much to reduce here. Now for this two-dimensional lattice, you can designate different points in the lattice with labels like this, and you can calculate the band structure, that is the E of k, that is how the energy depends on the wave vector from gamma to x, or from x to m, or from m to gamma, or whatever. You can you have different directions to calculate the band structure, and you have different panels here. That's how the typical band structure will look like. This is of course in the free electron situation. So here you can see the Fermi level will lie here. That's the Fermi level is the pink line here, and you can notice that in the subsequent examples the Fermi level will keep moving up, because the radius of the as the radius of the Fermi level the radius of the Fermi circle keeps increasing, in the band structure as well the EF will keep moving up. So here you can see the EF line is here. It cuts bands in the first Brillouin zone, and the band in this panel m to gamma, it cuts almost halfway. You have, this is filled, all these levels will be filled and all these levels will be empty, and here you can see all these levels are filled and a little bit of this blue line is empty. And this is the repeated zone depiction, and all the you're basically repeating it in all the zones, and you can see here you have the circles in all the first Brillouin zones. This is the second zone, third zone, and fourth zone, and so on. You will see these fill up in subsequent examples. So now we consider 2 electrons per unit cell or 2 electrons per site. So Z in this expression will be 2. Now the Fermi radius has become much bigger, and you can see that it actually extends into the second Brillouin zone, and you have this small segment that's in this pink region. So you can take this pink region and reduce it by a reciprocal lattice vector and push it down here. This one gets reduced here, this goes down, and that goes on top, and that's the reduced scheme here. You can also see the parts of the Fermi circle in the first zone as well, Fermi surface in the first zone as well. That's the first thing in the first zone, the blue line. This is the reduced part from the second zone. All of them are reduced into the first zone, shown reduced. So to understand how this works, so now you have this expression, and if we have Z equal to 1, that is 1 electron per primitive cell, that's what we just saw. The Fermi circle lies entirely inside the first zone. K of A by pi is 0.79, and if I make Z equal to 2, then you have this kind of a picture. You can see here that because this K of A is 1.128, so you can see here, this is, if I start increasing if I start populating from K equal to 0 all the way up to Kf, you can see this region will get populated first. There will be this small section will be empty, but this regions will get populated first, because the Kf from the center to just outside this boundary is smaller than this diagonal. So this region outside will get populated first compared to that. That is the reason why so what does this mean? Let me come back here. That is the reason why if I have this kind of a band structure, I have it gets populated up to this point, but there's a band overlap. So this band overlaps with that band. So the levels here are lower than the empty levels here. That's why these levels get populated first, and you have levels here empty, and that's where you have a semi-metal like situation. So for this particular case, you have here, you can see the Fermi level has moved up now. It cuts one band in the first zone, that's the blue line, and then it cuts one band in the second zone, which is the red line. You can see the depiction, red or pink is the second zone. So that line corresponds to the second zone. So the Fermi level cuts two bands. That's why I said there's a band overlap. The Fermi level is here. It cuts one band in the first zone and one band in the second zone. and some levels in the second zone are lower than some levels in the on the topmost levels in the first zone, so they get populated first, and that's the kind of picture you have. So you can have like I just said, hole like conduction in this zone because you have only a few levels open. You can think of those holes conducting instead of the electrons, and here you have electron like conduction. And in a metal it's possible. In the Drude model we saw that the Hall coefficient for some metals was negative, for positive, sorry. Even for a metal it was positive, the thermopower was positive. That is because you can have, you can have hole like conduction even in a metal because of the way in which the bands overlap with each other. Now we go on to, before we go on to 3 electrons, now you can see that this is the repeated zone scheme in the first zone and in the second zone. So you have all these fancy looking patterns. Some people call it a cigar shaped pattern, and what all kind of patterns can be found in when you do a repeated zone scheme. So you can take a moment to understand why you see this. You go back here and you can see, like I said, you take this portion and reduce it inside here. You take this portion and reduce it inside here, this portion here, that portion there, and that's how you get this. This is the reduced scheme, reduced zone. And in the repeated zone, you can see that's shown for the second zone separately, and that's shown for the first zone separately. Now for 3 electrons per unit cell, or 3 electrons per site, the Fermi circle is much more bigger, and it just intersects this boundary here. It doesn't go into the it doesn't go into the third zone or the fourth zone. It just stays on the boundary, and you have a reduced zone scheme which looks like this. So in this case, you can see that the Fermi level does not cut the bands in the first zone. It just stays, it's just above them, but it cuts a band in the second zone. The red line, it cuts the red band, but it does not cut the blue bands. And therefore, there is no, essentially in the first Brillouin zone, you basically have a point, you just have a dot, just to represent that it's, it just cuts very, very small, maybe one state or few states there. And that's shown as a small point in the repeated zone scheme. And in for the second zone, you have this kind of a picture. It takes some time for you to appreciate it. Please watch the videos again. Please play with this, the link, with the attached link. Then you will be able to get a much better understanding of what happens. Now, finally, for 4 electrons per unit cell or 4 electrons per site, this is the this is a screenshot from Kittel, and this corresponds to this example here. Now you can see that the Fermi level Fermi circle is so large that it actually cuts across 4 zones. It cuts the 4th zone, the 3rd zone, the 2nd zone, and it completely engulfs the first zone. And therefore, the reduced zone scheme is quite complex. And you can see this is the repeated scheme. You have this section in the 2nd zone, this section in the 3rd zone, that section in the 4th zone, and so on. And you can also, I forgot to include the band structure for this. You can check the website and play along and see what happens for the band structure for the 4 electron per unit cell case. Now, we had so far considered free electron Fermi surfaces in 2 dimensions. Now, what happens to the Fermi surface for a nearly free electron? Now, we had seen in the previous classes that this nice parabola for the free electron situation, when the k vector hits the zone boundary, when k equal to capital K by 2, then there is an energy gap and the bands get deformed like this, and you have 2 values of the energy here for that particular value of k, and you can see that the band here, if you actually it actually hits the zone boundary perpendicular. It's actually perpendicular to the zone boundary at the zone boundary. So if you have this free electron situation where you draw the Fermi circle and you have a zone boundary here, this is the free electron case we saw. But if I turn on the periodic potential just at the zone boundary, then to comply with this with this band's split, the Fermi level also gets split like this, and the energy must be perpendicular to this to the zone wall here, just like this. You can see the curvature of this has to be similar to this, and it's perpendicular there, and so this gets split. So you have one because of this energy gap formation, you have two distinct values of energy. The Fermi surface also gets split, and you have one segment here and another segment here. You can calculate the values of the radius if you want. If you using a simple argument, you can see it's a problem in Ashcroft. You can have a look at it. Now we had seen this kind of an example for 4 electrons per unit cell. You have the first zone is completely full, it's inert, so you don't need to worry about it. In the reduced zone scheme, you have the second zone here, that's the third zone, and you have the sharp edges. That sharp edges, when you turn on the lattice potential, becomes blunt, and you have this kind of a picture here. Of course, it's too hard for us to show how this happens and so on, but this is the kind of picture you have, and all these edges become nicely blunt and rounded. So what you're seeing here, this edge is actually this edge. I have just if I join 4 edges like this, if I plot at the center of this point and shift it here, I will get this kind of a picture. So if just to make that clear, let me just go back here. If you see this is the segment. This becomes nicely rounded because of the periodic potential and becomes like this. And you can see the gradient of the surface is pointed in both directions, both second zone and third zone. Sorry. Now we can do some dynamics with this. So given this expression for the for the force, that is the force corresponding to a magnetic field or an electric field. Now we just saw that when there is a magnetic field present, the electron moves on a constant energy surface. So for these two, if I, instead of drawing this difficult orbit of an electron, if I just draw simple circular orbits, you can see here this dk by this is the dk by dt, and this is the gradient pointing outside, and this would be the electron orbit. This is how the electron orbits in this case, and this is how the electron orbits in this case. Now this particular situation is called an electron orbit because this corresponds to the direction of an free electron orbit. How a free electron would travel when a magnetic field is applied, it corresponds to that, and therefore this is called an electron orbit, whereas this is opposite to that direction, and therefore this is called a hole orbit. So if I go back here, you basically have you have this situation where the field levels are the lower energy levels, and this is the higher energy level here, and these again the field levels are the lower energy levels, and this corresponds to an electron orbit. When I say orbit, in the presence of a periodic potential, the orbit doesn't mean circular orbit in the presence of a magnetic field. It's just it's a closed orbit, but the orbit depends on the shape of the Fermi surface in 2 dimensions or 3 dimensions. So this is a closed this will be how the electron will orbit around this surface on this constant energy surface in this path in the presence of a magnetic field, and this direction is similar to the direction of a free electron. That is not literally the path is not literally the same, but the direction will be the same, and therefore this is called an electron orbit, and the direction here is opposite, and therefore this is called a hole orbit. Now, depending on the nature of the Fermi surface, there can also be situations where the Fermi the Fermi surface looks like this in one zone, and then the other zone it looks like that, and so on. And therefore, you have a situation where the electron, there is no closed orbit, and you have an open orbit in the sense that in the reduced zone scheme, it will look like the electron goes in the presence of a magnetic field. It starts here and travels here, and then comes back again here. It basically follows the Born-Von-Karman boundary condition. It starts here, goes here, it hits the zone boundary, and then starts back again here, and so on. But in the periodic zone scheme, it will look like it just keeps traveling. It's not closed. the orbit here or here is closed. Instead of that, you have something called open orbits. It's not circular here, but it's closed. But here it's not open. It's not closed, and it's an open orbit, and the electron can simply travel in the presence of a magnetic field, I'm saying. So you have a complex Fermi structure like this in the repeated zone scheme. You can see that the electron can simply just keeps passing like that. It doesn't circle around like you have in the case of a free electron. Another example is shown here. It again is a very complex Fermi surface. I think this is copper, or I forget what the Fermi surface is. You have the electron can simply travel like this. So in such a situation, it can be shown that these kind of open orbits increase the magnetoresistance of the material, and we saw that in the case of when we studied the Hall effect. In the Drude model, the resistance of a material does not change with magnetic field. However, because of open orbits, because of the possibility of open orbits, we can show that the resistance increases when there are open orbits present. I'm not explicitly proving that, but I'll just state it as a fact that the resistance increases in the case of an open orbit. Closed orbits, they behave similar to the classical case, but open orbits are possible, first of all, when you consider the Fermi surface and how the electron travels on the Fermi surface, and on these open orbits increase the resistance of the material. That is, higher the magnetic field, higher will be the resistance. Now, coming to the dynamics in the case of an electric field. Now, we just saw that the velocity is basically the gradient of the band. So it's basically the derivative of the band, dE by dk. So if I plot the energy band for simple energy band like this, then the velocity will look like this. And this is a crazy looking graph, because we know that when you apply an electric field, the electrons get accelerated. That means that the velocity should keep increasing, but that doesn't happen. You can see here in the case of a periodic potential, the velocity as you travel from k equal to 0, that is from the zone center, and as you reach the zone boundary, at the center of the zone boundary, yes, there's a nice increase in velocity. The velocity increases linearly, it behaves classically, because you know that in the zone boundary we have assumed that the periodic potential is 0. That's the nearly free electron approximation. But as you depart from the zone boundary, the velocity keeps increasing. There is acceleration, yes, but then something astonishing happens. The velocity actually plateaus, and then as you approach the zone boundary, the velocity decreases. That is, there is deceleration, and the velocity actually becomes 0 at the zone boundary, and then it goes in the opposite direction. It actually looks like you are applying a static electric field, and for some k values there is acceleration, and for some k values there is deceleration, back and forth. It actually looks like a sinusoidal behavior in the presence of a static electric field. This is because when you are away from the zone boundary in the center, the electric field is able to effectively impart momentum to the electrons. But as the electron heads close to the zone boundary, the electron imparts more momentum to the periodic potential, and because of that it decelerates. There's a loss of momentum, it decelerates, and because of that the velocity drops down. So there's a very neat way of understanding electrons and whole picture in a very simplistic way, and you can also understand that the states near the zone boundary actually behave like holes, and to do that, so this is the current density that we just saw, and we can simply say that this current density is can be simply written as this is an integration over the first Brillouin zone, but you only consider the occupied states, because the unoccupied states are not going to result in any current. Only the occupied states are electrons will result in the current density. But we just saw that if the entire if I consider the entire energy band, that is, if I consider the occupied states and the unoccupied states, that is, if I integrate over the entire zone, then the current is zero, because if all the energy states are filled, then some of them will have positive velocity, some of them will have negative velocity, there will be no current. So if I do the integration over the entire zone, then the current density would be zero, and that I can just equate it as the current from the occupied states and the current from the unoccupied states, and that sum should be anyway zero. And I can rewrite this as, I can just invert this equation and write the current density as arising from a positive charge and from the unoccupied state. So this is like saying, this is the current density from electrons, this is the current density from holes. So instead of, this is the classic argument you must have done. If I have 10 states and 2 of them are empty, and there are 8 electrons and 2 of them are empty, instead of looking at the current from the 8 electrons, which is this, which is the occupied states, I can look at the current from the 2 empty states, but I just change the sign of the charge to account for the fact that they are empty, and that's the current from the unoccupied states. Whether I use this picture or this picture, the physics will be the same. That's the whole picture. So you are able to you are able to find a way to account for holes using band structure, using this simple semi-classical model. But you must not use both the electron picture and hole picture for the same band. For a given band, you must either work in the hole picture, you must either use holes as carriers or you must use electrons as carriers. If you mix them, then it's wrong, because if you mix them anyway, the current should be zero, because the total current due to both should effectively be zero, as we just saw. Finally, we can also look at the acceleration of the electron. So we saw the expression for the velocity to be given that. We can calculate the acceleration in this fashion, and I can rewrite this and pull out dk by dt outside, and the force is h cross dk by dt. So I can substitute for dk by dt in terms of the force here, and I can now write the force as something times dv by dt, and this term here is basically, you can think of it as a mass, and that's called m star, as that's called the effective mass. This is the mass of a block electron in a periodic potential. So that 1 by m star is defined to be this, and so given an energy band like this, so you have an energy band of this fashion. So you take the first derivative, you get the velocity. If you take the second derivative, you can calculate the effective mass, and you can see here in this close to the zone center, you have the positive effective mass, and then after the velocity plateaus here, you have a peak, and then the velocity stops decreasing. That's when the momentum transfer happens to the lattice. So the effective mass actually changes sign, and then you have negative effective mass. And so for states that are close to the zone boundary, they actually behave like holes. So a negative effective mass means that on going from state k to k plus delta k, the momentum transfer to the lattice from the electron is larger than the momentum transfer from the applied force or the applied field to the electron, and that's the reason why you have negative effective mass, and you have and you need to sometimes it's convenient for you to consider states close to the zone boundary in terms of holes. You don't need to do it all the time. For example, if I have this kind of situation where the band is only half filled, then I can use electrons. But if the band is like 3/4 filled, if the filling stage is up to here, then only few states are empty. Then instead of considering the transport by electrons, I can consider the transport by holes as well. So that's about that for the semi-classical perspective of the semi-classical picture. We will go on to other things in the next class.